So n here for us is -4. And just use the formula. So what's going to be out front? -4. X to the -4 minus 1. So be careful with that. That's -4x to what? -5. And that's the same as -4 over x to the 5th. You could just take that, drop it down.
You say take that drop down, you're saying drop the -4 down?
Nope, -4 is on top. This, remember, anything to a negative power, you can drop it down and it becomes a positive power. So this is just a property of exponents. X to the negative n is 1 over x to the positive n. All right, power rule's good, right? And we move on. Next rule. The constant multiple rule. This one always confuses students. I think it's because of the notation. So I'm going to just read this out, and then I'm going to do an example. I think it'll illustrate what this is saying. If you're trying to take the derivative of a constant times a function, then you can just bring the constant out and take the derivative of the function. Okay, so let me do an example. We want to find the derivative of this. All right, do you see that we have a constant in front of x cubed?
Yes.
Right? This rule is saying that what we can do to find the derivative is just bring the constant with us, okay? It's just going to come with us. That constant's going to come with us. We're not going to change it. And then we multiply that times the derivative of this. And what's the derivative of x cubed? 3x squared, right? 3 comes down, subtract 1 from 3, you get 2. So am I pushing too far for everyone to see that that's that now without doing any writing on the board? You all right with that? So what's my final answer then? 12x squared. Done. Questions on that? Yes. This is a constant, right? Times some function. X cubed is a function. The rule says if you're going to take the derivative of that, just bring the constant in front. Okay, so just bring the constant and then take the derivative of this piece. The derivative of that is power rule. So the 3 comes out and we subtract 1 from 3 and you get 2. Right?
Yeah.
But the constant came with us. But wait a minute. I thought I said the derivative of a constant was 0. I thought I said that. Didn't I?
Yes.
So what's going on here? When it's just a constant by itself, the derivative is 0. But when the constant is attached to a function, what happens to it? It just comes for the ride. All right? There's a big distinction there. Derivative, if I ask you what's derivative of 10, you're going to tell me 0, right? But if I take that 10 and attach it to a function, then it's no longer 0. But the 10 will come with us for the ride.
This is that tip that you showed us.
Yes.
Like a few days
Yep,
ago.
yep. This is basically it. So now let's do another one. How about this? You have 8 in front of the square root of x, right? And I want the derivative. So the 8 is being multiplied times this. So when I take the derivative, the 8 is coming for the ride, right? So I already know that my derivative is going to have 8 sitting there. Now I have to look at this and take the derivative of that. So it might be worth it for you to see if you can take the derivative of that. That's the same as what? X to the 1/2, right? So now your n is 1/2. So when I take derivative of that, what happens? 1/2 comes out, right? Then x to the 1/2 take away 1, which is going to be -1/2. So what do we get here? What's this? 4 x to the -1/2. But that's the same as 4 over what? x to the positive 1/2, but that's the same as 4 over square root of x. If you have a constant in front of a function and you take the derivative, the constant's coming for the ride, right? Now, if something else happens, like a 1/2 pops out, then yeah, you've got to put the constants together and make a new constant. But the 8 didn't change, right? Questions? I want to do one more, but it's not using this rule. I just want everyone to look at this one right here. We just did this one with 8 in front of it, right? But this comes up a lot, right? A lot of times in this class and in Cal 2, you need to be able to take the derivative of the square root of x. Just pops up a lot. So I'm going to show us, let's do the power rule on it, let's get an answer, and then we're going to memorize that answer. Because it happens so often, we don't want to be doing this every single time. So first of all, let's rewrite it as a power. So this is same as x to the half, right? So what would my derivative be here? 1/2 x to the negative 1/2. It's basically what we just did here, right? But there's no 8 in front. Now, please see if you follow me on this. Negative exponent, I'm dropping it down. But 2's already down there, isn't it? So it joins the 2. And then I'm going to write that as 1 over 2 root x. That's what it is, right? Okay, please memorize this. The derivative of x, right, is what? 1 over 2 root x. The derivative of x is 1 over 2 root x. No? You don't agree? Oh, sorry. Yeah, did I say x? I just said x. I'm an idiot. Just ignore everything I say up here, please. The derivative of the square root of x is 1 over 2 root x. The derivative of the square root of x is 1 over 2 root x. All right? Don't go through this work every time now. Just for this one. Okay, this is a very special one. If you ever see that, just go right to that and be done. All right? What's the next rule?
Would his root be 1 over 3 root x?
No, it would not. Good question. The question was, if this was cube root, then would that be 1 over 3 cube root x? I think that's what you're asking, right?
Yeah.
It would not, because if you took the derivative here, you would get 1/3, right? That part's good. That would give you the 1/3. But when you subtract 1 from that, you get negative 2/3. So this would be 3. This would not be 1/3, it would be 2/3. And so you would get the cube root of x squared, and that would be a 3. So it doesn't follow that. Yeah, it only works that way for the square root. Next rule. The sum and difference rule. This is a very nice rule, and you should be happy to see it. It looks complicated, but it's really not. It just says, look, let's say you're trying to take the derivative, and you've got some function being added to another function, or some function being subtracted. So we have terms. We have, let's say, 2 terms. When we take the derivative, we can do them individually. We can take the derivative of the first one, and then just add or subtract, depending on if it was add or subtract, the derivative of the second one, and that's our answer. So it works the way you would hope it would work. Let's do an example of this. Let's say I have 5x minus 2x to the 7th, and we're asked to find y prime. Right. So do I have 2 functions of x separated by addition or subtraction? Yes. Since I do, I can take the derivative of these individually, separately, and then just slap a minus sign between them. So what is the derivative of 5x? This will be interesting to see. 5, why is it just 5? Because the 5 will come for the ride, right? 5 will come for the ride. And what is the derivative of x? 1. Right? We did that. That was the second rule I gave you. So the derivative of 5x is 5 minus, now what's the derivative of this one right here? So the 2 stays, but the 7 pops out. So that really turns into a 14. And then x to the 6th. And that's it. You're done. Understand? Yes?
I need you to explain to me, I know this is wrong, but I just want to know why. There's an understood exponent of a 0 in the 5x, correct? Wouldn't that be coming?
This would be an understood exponent as a 1 right there.
Okay.
Right?
Yeah,
And it and it works that way.
That one would
Yeah, because it multiplies.
Right? Because it comes out 1, but then it comes x to the 0.
Got it.
What's being brought up is, let's say we brought the 5 down, right? And then we use the power rule on that. Right? The 1 would come down, x, and then we would subtract 1 from the power, would be 1 minus 1 is 0. But x to the 0 is 1, so this turns out to be 1. So it still works. But don't use the power rule for x. Just use the fact that the derivative of x is 1. One more example. I think I'm going to get you on this one. Find the derivative of that. All right. Can I show you the mistake? Let me show you the mistake. I hate showing mistakes, but let me show you what is not correct here. Everyone paying attention? I know it's Thursday. You want the weekend to be here, okay? But these are the fundamentals of taking derivatives, and you cannot jog or run unless you know how to walk, and this is walking, all right? So what people do wrong is they say, oh, I'll just take derivative of that, that, and that, all separately. You're not allowed to do that. We have not talked about how to take the derivative when you have two things divided like this. We have not talked about that. We've only said if it's a constant by itself, the derivative is 0. We said if it's x to a power, we do a power rule. We said if there's a constant in front of a function, you can bring the constant for the ride. We have not talked about division at all. We talked about addition and subtraction, but the problem is, yeah, we've got addition and subtraction, but we've got division too. So the only way to do this problem right now for us is to realize that we have 3 terms in the numerator and 1 term in the denominator, and algebraically, you are allowed to split this up into 3 terms. Right? Fractions work this way. That is allowed. And you should know that because, look, if I asked you to put all these together, you could, right? You could squish these together because they all have the same denominator. And so it would go up to that, right? So backwards would be this. And that's what we just did. We're just ripping it all apart. Now you can only do that if there's 1 term down here. If there were 2 terms, you can't do it. It wouldn't work this way. Now, each of these, we can take the derivative of each of those separately. But you have to make these look like powers of x first. And they don't look like powers of x. It's x over x something, right? So we have to clean this up still. I'm not taking the derivative at all right now. All I am doing is cleaning this thing up, or I guess changing what it looks like. So all I did was rewrote my roots as to the 1/2, and then I'm going to put these together like this. This, and that one I'm just going to pop up. Just going to move it up. So what does the first one become? 5 what? X to the 1/2. And you got 1/2 from doing what? Yeah, 1 minus 1/2 is 1/2. Okay? Then minus 3, and then you go 2 minus 1/2. 2 minus 1/2? 3/2. Right? 3/2. 2 minus a half is 4 over 2 minus a half, which is 3 over 2. Right? You have to get a common denominator to just subtract these. And then the last one, this just comes up, so it's x to what power? Negative half, because it was positive down here. To move it back up, it becomes negative.
Not use the x for negative 3.
I didn't want what? Oh, yeah. Where's my x? Is that why y'all were squinting? Yeah, I should probably have an x here, huh? Yeah. Thank you for pointing that out. I think I would have realized at the next step when I tried to take the derivative. Okay, so do we all agree that this right here is y? That's the original function. I've taken no derivatives. All I've done is massaged it into something that I can take the derivative of. And now I can use the rules. The rules say that if you have addition and subtraction between things, you can do them individually. And then as I look at this, I have a constant times this. Constant will come for the ride, power rule. Constant will come for the ride, power rule. Well, there's a 1 out here, I guess you could say. Power rule in this one. So I have 3 power rules to do. Here it comes. Y prime is, okay, let's try and do this without writing too many steps. This 1/2 comes out like that, right? And hits that 5 and becomes what? 5 halves, right? 5 halves, like that. I heard 2.5. That is correct, but this is called a mixed number. And this is called an improper fraction. And now that you are in calculus, we don't use those anymore. This is like, you remember when we used to use the division symbol and that's what we used? Do you remember when multiplication was this? Right? Okay, mixed numbers is kind of like that. All right? Improper fractions are more advanced because well, shoot, look at the power rule. We have to be subtracting in fractions and subtracting 1 and all that stuff, right? We have to be very comfortable working with improper fractions as opposed to these. I know some people like these, but I'm telling you, go open up any engineering book, any physics book, you are no longer going to see mixed numbers, right? They're just going to go away. They just vanished. They're nowhere in this book, I can tell you that. So we want to get used to this. Here, yes, x to what power? Negative 1/2. Okay. Now, here to here. It's negative 9 over 2. So you're multiplying 3 halves times 3, negative 9 halves, right? And then x to what power? So 3 take away 1, or 3 halves take away 1 is what I meant to say, 1/2. And then finally, what happens here when we bring this out? Just becomes a negative, right? So that plus becomes a minus, 1/2 x to what power? We're taking away 1 from this, minus 3 halves. You are going to have to get real comfortable subtracting 1 from different fractions, okay? Because you have to do it all the time here. So even though I'm moving a little fast here, I'm trusting that you can go from here to here by just subtracting 1 from those fractions. And you'll have time to practice in your homework. All right, we're doing good, we're doing good. Let's see the next rule. Or I think we might be done with rules. Oh, no, okay, so these aren't rules. These are just, I guess they're rules, but they're very specific to specific functions. And I think I showed you this. I tried to convince you geometrically that the derivative of sine was cosine. Do you remember me trying to convince you of that? Yeah? Now I'm going to prove it to you. So you all ready for me to prove this? Okay, good. I'm going to. I want to show right now that if f of x is equal to sine x, I want to show you that the derivative of it is this, cosine x. Right? Here it comes. What is f prime of x? Well, we have to go back to the limit, don't we? This good old definition. keep in mind, after I'm done proving this to you, you never have to prove this to me at all, ever. You need to know that the derivative of sine of x is cosine x. But as a student of calculus, I think you should see some of these things proven, all right? So what would this next line be, or next step? Limit h goes to 0. What is this? Sine of x plus h, right? That's plugging x plus h into the function. Then minus what? Sine of x. And then all of that over h. Now, at this point, we kind of get jammed up a little bit because there's not much that you can do. Like, right? Like this right here. Like that. That is not this, right? Right? That is major. No, you cannot distribute sine through. It doesn't work that way, right? So we kind of run into a problem of how do we actually simplify this to make an h cancel? Like, how can I make an h cancel when that h is trapped inside the sine function, right? Okay. So does anybody recognize this at all from pre-cal? And while you're thinking, I'm going to write some stuff down here. There was something in pre-cal. What was it? I thought I heard it. Some difference formulas. And pre-cal, so who has their formula sheets? Can I see those? On your formula sheets, there are different formulas here. Where's the trig one? On reference page 2, on the right-hand side, there's they call them the addition and subtraction formulas for sine. It says here, I'm going to write it down. Sine of x plus y is equal to sine x cosine y plus cosine x sine y. Okay, does that look familiar to you from pre-cal?
Yes.
All right, so if I use that formula here, what would this become? This would become what? Sine x cosine what? H plus cosine x sine h. Right? That's what this would become from pre-cal. And then minus sine x. All over h. Now, that still does not allow me to cancel an h, because this h is trapped in the sine, this h is trapped in the sine, this doesn't even have an h, so there's no canceling, right? I can't do anything yet. But I'm going to do something very clever now. When I say clever, it's not me, okay? I'm not clever. Someone showed this to me, and now I'm showing you, all right? So sine x cosine h, well, I'm clever sometimes, but to be a math major, you have to be clever at some point. But I didn't come up with this. Okay, so what did I just do? What did I do here? I took this one right here and I just popped it right over here because it's addition and subtraction. So I moved it next to these two, right? And then I split it into two fractions. So I could put these back together, right? And I would get back that. So you all agree this is true? Okay, now watch this. Limit h goes to 0. Okay, let's look at this first one. See how this has a sine x in it and a sine x in it? Right? I'm going to factor it out. Sine x times cosine h minus 1 over h. So in other words, if I pull this sine from here and here, bring it out front, then if I want to multiply these together, I would get this times this, and that would give me back the top there. So algebraically, these are the same, aren't they? And then on this one, I'm not factoring anything out. I'm just kind of rewriting it in a way that will hopefully make something that happens next apparent to you. This is the same as that, right? Okay. Now, we are going to try now to let h go to 0. Does h have any impact on that? No. So that's going to stay. Does h have any impact on this? No, it's going to stay. All right, let's start over here. What's that? Let h go to 0. Not undefined. Junk over junk. That's sine of junk over junk. That goes to 1, doesn't it? That goes to 1. So when I take the limit, this is not changing. That's going to stay cosine x. And this, we already, well, I never showed it to you. I told you to believe it, didn't I? And I told you later I would show it to you. I'm still not ready to show it to you. Okay, so you have to believe that that goes to 1, and now you get cosine x plus over here. Now this one was, there were two formulas I said you should know. This was one of them. This was the other one. Does anyone remember what that one goes to? 0. So this one goes to 0, and then times sine x over here. And then this goes away, and all you're left with is what? Cosine x. So the derivative of sine x is cosine x. All right? Yes?
That one on the left that you circled, that one goes to 0 because the cosine of x minus 1 equals 0, and it's the other property, right? Or no? Am I thinking something else?
I'm not sure what you're thinking, actually.
It's saying if sine of h, or sine of junk over junk is equivalent to 1, then the other property equivalent to that was the cosine property, where it just goes to 0.
Well, there were two formulas, right?
Yeah.
Yes. There were two. One of them went to 1, the other one went to 0, but I never justified why this does this. And we still don't know why these two do these things. I'll clear it up later, but you're going to have to wait a couple of weeks before that happens. All right, so is that convincing enough? The derivative of sine of x is cosine x. Now guess what? We could do the same thing for cosine. And if we set up the limit for cosine, the only difference, we'd have cosine of x plus h minus cosine x. Then we would use the formula for cosine the same sort of way. We'd play the same game. But it would work out a little bit different, and you would get the next formula, which I'm not going to prove. And that is that the derivative of cosine x is negative sine x. Negative sine x. So it's not sine x, it's negative sine x. And you just have to remember that. And then there are 4 more. Because so far, I have the derivatives of the first two trig functions, right? Derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Those two burned, okay? Next week, those are burned in already, all right? Those get burned in this weekend. Burn number 8 in also. You should know, as a Cal 1 student, you should know. Why do they say by heart? Know by heart? You know by brain, right? Really? So you should know by brain next week. Derivative of sine is cosine. Derivative of cosine is negative sine. And the derivative of tangent x is secant squared x. I'll prove that to you later, not today. I will prove it to you, but we'll do something else. We'll be real clever the way we do that later. And then the next 3, you should just know that they exist on your formula sheets and reference them when needed. The derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. Derivative of cotangent x is negative cosecant squared x. These are all on your formula sheets, all right?
So that's all like 11?
All of them. I don't know if the power rule's there for sure. All the derivatives of the trig functions are there. I don't know if the derivative of constant 0 is there. I'm pretty sure derivative of x is 1 is there. But I'm saying you should have these memorized in terms of, like, you don't want to be in Cal 2 and they're like, what's the derivative of sine? You're like, hold on, let me look at my formula sheet. You know, like, you won't actually make it to Cal 2 if you can't remember that. Okay. So let me just look real quick. You want me to go back? Oh, these are, okay, I'll just leave it there. Okay, y'all can, I need to get an example going here. If y equals x minus 2 cosine x, find when the tangent, or I should say where. Find where the tangent lines are horizontal. I'm going to graph this. That is the graph of x minus 2 cosine x. All right? Bless you. I would like for you to tell me where the tangent lines are horizontal. That means I want you to tell me at what x value would I go to the graph and find a horizontal tangent line. So horizontal means flat, right? So slope would have to be what, 0? So I'm talking about like right here. You see how the slope of the tangent line is 0 there? I'd like to know where that happens. I also want to know where that one happens, and that one, and that one, and all of them, because there's an infinite number of them, right? So where are they? Where do they happen?
Is it like a formula for it?
No, we have to, that's what we have to figure out, okay? So I know I'm jumping from basic formulas to this idea, but this is what it's all about. I have a graph, and I want to know where my tangent lines flatten out on this graph, which would correspond to all these peaks and valleys, right? So how do we do that? Well, we just think about what it means. What does it mean to have a horizontal tangent line? And you already said that. What does that mean? Horizontal tangent means that my derivative has to be 0, right? Because the derivative is the slope of the tangent line. That's what this is asking me to do, right? To find where the tangent lines are horizontal is equivalent to me asking you where the derivative is 0, right? Okay, so let's take a look at the function and let's see if we can find its derivative. So what is the derivative? And you know what? I'm using y here, so I'll use y prime equals 0. That's what we want to know, right? Question mark. When is that derivative 0? So let's get the derivative. All right, well, we have subtraction, right, between these two things. So I can do them individually. What's the derivative of x? 1, thank you. Okay, now minus 2 is going to come for the ride because it's a constant sitting in front of a function. What is the derivative of cosine of x? Negative sine of x. So I'm going to write it like this. And you have to be careful there because you're not saying negative 2 minus sine x. You're saying negative 2 times negative x, or negative sine x. So we have y prime equals 1, what? So we have minus, but then this is going to be negative, right? So won't be plus 2 sine x? Yeah. Because imagine this was like negative x, right? Then it would be minus negative 2x, which would be plus 2x. So the important thing is there's multiplication. So you're taking a negative times a negative would be plus. Y'all okay with that? Now, I want to know when that's 0. Right? When is this 0? So what do? You set it equal to 0. Right? That's what you do. And that's what you do in pre-cal. This is a trigonometric equation. You want to solve it. Now we get to see how much trig you remember. So how can I solve this trig equation? Do what? What do you mean 1/2? I'm not sure.
Like you'll subtract the 1.
Okay, so subtract 1. Let's subtract 1 on both sides. And then divide by 2. So what you're saying to yourself is, and this is where I really just wish I could get into each of your brains to see how you think of this. Because the way you learn this is important. This can be either very easy or very hard depending on how you learned it. If you didn't learn it right, it's going to be hard. So here's the way that I present it to my class. Let's see how many of you like buy into this and understand it the same way. When I think of the trig functions, sine and cosine, I always think of a unit circle. And so what we're saying here is, at what angle is our sine equal to -1/2? So sine always corresponds to either the x or the y coordinate on the unit circle. Which one is it? The y coordinate, right? So where on my unit circle is my y coordinate -1/2? Here, because it's actually √3/2 -1/2, right? So sine is the y coordinate, so it's there, right? So it's that, but that's not the only place. Over here, because the coordinates here are -√3/2 -1/2. So we have two places, right? Now from the picture that we had just a second ago, it looked like this weird saw blade looking thing, we should have an infinite number of answers. An infinite number of answers. This is two of them. How do we get all infinitely many? So again, I'm asking this because I don't know how you learned it. So I look at these two, and what I need to do is find what we call their general solutions. So I'm going to start with this one right here. What is this angle right here, from there to there?
210.
Let's do it in radians. 7 pi over 6? I thought you said you didn't remember pre-cal. Oh, you got it right there. Okay, good. All right. Okay, so this, remember, we're trying to find sine x equals -1/2, right? We're trying to find x, which is an angle, right? The angle that gives us -1/2 on the unit circle. So my x's have to be 7 pi over 6, right? Would be one answer. But what's another answer I could have had? Not ignore this one for now. I could have gone, how about I go around one time and then come all the way back to it? So do one full revolution first, then come back to it. Or what if I did like 2 revolutions and then back to it, right? Or 3. So all we have to do here to get our general solution is add to this a full rotation, which is 2 pi, and then we use n or k depending on your instructor. We'll use n? K? K? Ken or A? Ken or A? What? Ken or A? N or K? Okay, N or K. It doesn't matter which one you use here. We'll take a vote. K? Most of you use K. I use N a lot, but okay, let's do K. K, but what is K? It's important that we state what K is here. K is any integer. Okay, what's an integer? What is an integer? What are the integers? 1, 2, 3, 4, 5, 6, but also -1, -2, and 0. So it's all like your counting numbers, both positive and negative, and 0. So you're taking out all the little decimal fractions and stuff in the middle. So as long as you're adding either like 0, no rotations, then you have that answer. If you add one of these rotations, then plus the 7 pi over 6, you'll get one answer. So this is an infinite number of answers, right? Okay. That just took care of this one. Or x is, now what's this angle right here? In radians. I'm only saying radians because we really start to walk away from degrees in this class. We do radians almost exclusively. 11 pi over 6. So 11 pi over 6 takes us here. If you wanted to, you could just use negative pi over 6. It's up to you. But I'll use 11 pi over 6. So 11 pi over 6 plus 2 pi k again, right? Because we could start here, and then we could add a full revolution, and we'd be back at the same place. So these are our general solutions, right? We're done, but I want to just show you one more thing here. Okay, tell me what I did right there, and tell me what I did right here. I just got a common denominator between these. I had this over 1 This over 1, I wanted to put them together, right? So I put 6 on top and bottom here, 6 on top and bottom here, and then I put them together, I got this. The reason I did that is because it's very easy right now, if I have it in this form, to just start plugging in values of k. Like right now, if I ask you to plug in, we're almost out of time. If I ask you to plug in k as 0, if k is 0, what are the two solutions we get? If k is 0, let's try this one. If k is 0, it's just these two, right? So we get 7 pi over 6 and 11 pi over 6. But what if k is 1? Well, then you have to do, what, 2 pi plus this? So you have to get a common denominator and put them together. 2 pi plus this, common denominator. But if you write it in this form instead, it's already put together. So if I put 1 in here, what would I get? 7 pi plus 12 pi, 19 pi over 6. And this one would be 23 pi over 6. And then if k was 2, see how easy it is to get from here? So 2 in here, I have 24 of these, plus 7 would be 31 pi over 6. And then the other one over here, 35 pi over 6. And I can keep going, right? All right, I have like 30 seconds. Let's go back to the graph here. Let's see if I don't know if we can get any of these points. Oh, look at that. Oh, wow, this thing's smart. Whoa, this computer is smart. Or this website is smart. Look at that. When I click on the graph, it shows all these points, right? And if you click on one of the points, it actually gives you the x-coordinate, 31 pi over 6, right? And that's on our list. So we actually found on that graph every single place where we have a peak and valley. All we had to do that was what? Set the derivative equal to 0. So this is going to come down to now, the game that we're going to play in this class is take a function, find its derivative, set it equal to 0, and then solve the equation. That might be a trig equation, might be a quadratic, might be who knows what, radical equation. Yes?
Kind of a roundabout question, but kind of like what are the expectations for like our ability to recall a complete unit circle? Because like I mean I could have probably phrased a unit circle and then gone to that, but I don't know if I was able to. Oh yeah, well.
I think, you know, the tests and quizzes are always going to be timed, right? So your ability to, you know, pull that information out of your head to know these two angles should be something you can do without having to recreate the whole circle. So it needs to be pretty proficient, I'd say. Because you don't want to take 10 minutes in the middle of a test drawing a circle. You want to know those angles and kind of know how they correspond to all the points. Just practice. Just go get your circle. Oh, right here. I put them on the table over there. All right, I'm going to shut it down. Y'all have a good weekend. I'm taking attendance off of the exam.